Hi, Malcolm, can you hear me? Okay, it sounds like we're good. I don't know if anybody else wants to test. I'm going to mute now.
Okay. Hello, everyone. Welcome to the King's College London Dark Matter Day event. I'm a musician. I'm not the chair, but I couldn't find a chair, so I'm just doing the chair for tonight, maybe. So tonight, we have 4 scientists explain about dark matter, its existence and theoretical and experimental feature. And after all talks, there will be some Q&A session. So you're welcome to post your question on the chat window, or you can wait until the end. Okay, so the first speaker is Dr. Miguel Campos. Miguel will explain the nature of dark matter, the darkness that surrounds us. Please, Miguel.
Hi, everybody. I hope you can hear me. Thanks a lot for joining us in this live stream today in Dark Matter Day 2020. My name is Miguel Campos, as Tepe introduced me. When I'm not a giant skull, this is how I look like, and I'm a research assistant at King's College London. And today, as he kindly introduced me, I'm going to talk about the darkness that surrounds us. And no, I'm not going to talk about 2020 or war politics. It's a different kind of darkness, the one I'm talking here. And hopefully by the end of my talk, you'll understand that this is actually a misnomer. I'm talking about, of course, dark matter. And what do we know about it? But let me start by quoting the great Carl Sagan. Everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives in a tiny speck of dust suspended in a sunbeam. Truth is, astronomy can be a really humbling discipline because it tells us that our place in the universe is really unexceptional. What I want to tell you today can also be very humbling because it reveals our ignorance about the universe. Everything we see, everything we know of, constitutes but a small fraction of everything there is. What do I mean by this? I'm going to explain soon. But first, I want to talk about the things we do see. Let's talk about light. Light, or electromagnetic radiation, can behave like a wave, like sound waves, for example, or the waves in the ocean. Unlike those examples, though, what oscillates is not the medium itself, but the electric and the magnetic fields. Like most waves, however, its defining property is its wavelength, which is simply the distance between two crests or two troughs. In this way, then, we can have light with very, very short wavelength, like X-rays or gamma rays, which have wavelengths as short as the size of atoms or atomic nuclei. If we move towards longer wavelengths, we find the visible spectrum, which is basically the colors that we see. This spectrum has really nothing special about it, except the fact that our eyes have evolved to be able to see it, which is no coincidence because visible light propagates very well in water, which is where our eyes evolved millions of years ago. If we move to longer wavelengths, we find microwaves and radio waves with wavelengths as long as cats and buildings. Another property that light shares with sound is that both experience the Doppler effect. When a source of electromagnetic radiation approaches to us as observers, we see a wavelength that is shorter than the one from the source, or bluer. When the source, on the other hand, is moving away from us, we observe a wavelength that is longer or redder than the one that the source actually has. This is what we call blue shift and red shift. Of course, for this effect to be noticeable, the source has to be moving with respect to us observers in the orders of hundreds of kilometers per second, because it has to be a velocity that has to be comparable to velocity of light. So with this short introduction, I'm now in condition to tell you about dark matter, or how we realized that we were missing 85% of matter. So our story brings us back to the 70s, when astronomer Vera Rubin started to analyze the rotation of galaxies. The thing is that we can learn a lot about a system this way. Take, for example, the solar system. Already in the 17th century, we know that the farthest a planet it is from the sun, the slower it moves. And if you're able to measure these velocities accurately, you can estimate the mass of the sun. In the same way, if you measure the velocities at which different parts of a rotating galaxy are moving with respect to the center, you can estimate the mass of the system. She achieved this feat by using the Doppler effect, by measuring the blue shift and the red shift of the different sides of a rotating galaxy with respect to us. And what she found out was incredible. She found that velocities flatten out after a certain distance from the center. This implies that the gravitational pull remains constant after a certain distance. But this should be impossible because we know for a fact that the number of stars and the amount of gas diminishes when you move farther away from the center. So the only reasonable explanation is that there is actually way more mass than the one we can actually see, in particular in galaxies. This implies that all galaxies, including our own, are embedded in these massive halos of this dark material. This is the darkness that surrounds us. Actually, as it turned out, a similar conclusion had already been drawn back in 1933, when Swiss astronomer Fritz Zwicky started to analyze the Coma cluster, which is a cluster of galaxies. He measured the different parts, the velocities at which the different galaxies were moving with respect to the center, and concluded that these velocities were too high and the system should have flown off long time ago. Sadly enough, his measurements were riddled with uncertainty, which prevented his results to be taken too seriously. However, he's credited to have coined the word we use today to describe this material, dark matter, or dunkle Materie in German. Of course, the fact or the idea that most of the material that makes up the universe doesn't emit any light was met with skepticism by the community. And astronomers tried to put forward every candidate they could think of to explain this phenomenon. Dead stars, rogue planets, coal gas, dust, you name it. They look for every possible candidate. Sadly enough, all of these possibilities were ruled out. And after this came the most convincing piece of evidence in favor of dark matter. But before I tell you about that, I have to make a small digression, and I have to tell you about gravitational lensing. One of Albert Einstein's breakthroughs is that he changed the way in which we understand space and time. There is a classical analogy to understand this concept, although be careful not to take it too seriously or too literally. In this analogy, space and time act as a fabric, and every massive object bends this fabric, like a bowling ball on a soft mattress. Then what we understand as gravity is simply the warping of this fabric. And everything has to follow the patterns of this warped material or this warped fabric, including light. So the more the massive the object, the more the light bends, acting effectively as a lens. This is what we call gravitational lensing. Let me put an example. Imagine a distant source of light, like a galaxy, and in between us and that source, a massive object, like a cluster of galaxies. The light from the source on its way to us gets bent, and the image gets mirrored or distorted. And in the extreme case, we can get multiple images of this object, of this source. This is what we can see here in this animation. So astronomers use this technique to map the distribution of mass, because the amount of mass is directly proportional to how much the light is bent. So you can use this effect to map the mass of a system. And astronomers use this technique to map the mass of a very special object called the bullet cluster. The bullet cluster owns its name to the fact that this is actually two clusters of galaxies that collided with each other long time ago. This object is located 3.5 billion light years away from us. When these clusters of galaxies smash against each other, the galaxies themselves, because they are so sparsely distributed, went through each other and impeded. However, most of the normal mass of the system of a cluster of galaxies is actually in the form of gas. And when these objects collided, the gas got so hot that it emits X-rays. And this is exactly what we observe thanks to the Chandra X-ray telescope. We can see that the gas has the shape of a shock wave, which is the result of the collision. However, using the technique of gravitational lensing, we can map where most of the mass of the system really is. This is what you can see in this picture. In magenta, you can see the X-ray, the hot X-ray emitting gas in the center, and on the sides with the galaxies where most of the mass really is, which is in accordance with the theory of dark matter. In order to see this even more clearly, a group from the Durham University simulated this collision and obtained exactly what we measure today. All their simulations, without including dark matter, failed to reproduce what the Chandra telescope observed. So by now, I'm going to assume that you're all very much convinced about the existence of dark matter. So what do we know about it then? Well, we know a few things. We know, for example, how it interacts. We know that it doesn't interact with light, which is why we call it dark, although a more accurate name will be invisible, which is admittedly less catchy. We also know that it interacts with gravitationally, which is why we call it matter. Both of these things you should know by now if you have been paying attention. But we know more. We know also how much of it there is. It turns out when we take into account all the matter in the universe, the visible matter or normal matter accounts for just 15% of all of it. This is all the matter that we know and love. So it turns out then that dark matter is 5 times as heavy as all the matter we know about. The final piece of knowledge that we have about dark matter reveals its importance. It turns out that it's essential to form the largest structures that we observe in the universe. When supercomputers became available, it started to become feasible to simulate how the universe has evolved from an early stage until today. This is what we observe in this simulation by a group in Stanford. Turns out that when you don't account for dark matter, large-scale structures like cluster or superclusters fail to form because of all the energy that is released during the early universe. But when you add dark matter, then these structures start to form and start to make these web-like patterns, which is exactly what we observe. Recently, just a few months ago, the the Sloan Digital Sky Survey released their latest dataset, which is plasmated in this video, which includes detailed measurements of more than 2 million galaxies, which reveal exactly the same pattern that we observe in the simulation. Maybe a bit less dramatic, but clearer, you can see in this image, where on one side we have the simulation, and at the other side we can see what we actually observe in the sky. This web-like pattern is what we call today the cosmic web, and dark matter is essential to form it. So we can think about it like some sort of cosmic glue. So that's all very nice. We know quite a few things about dark matter. However, there is a crucial piece of information that we don't know. We have absolutely no idea what it is. Actually, scratch that. Our problem currently is that we have too many theories that can explain for dark matter, especially in the field of particle physics. What these candidates are and how do we plan to measure them is the topic of the next 3 talks that I'm sure you will enjoy. So make sure to not close your tab just yet. Thank you.
Thank you. Thank you, Miguel. That was a great talk. The next speaker is Dr. Dodi Marsh. Dodi thinks the darkness surrounding us is a wave. It's a wave. Please, Dodi.
It's a wave. Okay, so thank you all for being here. And I'm going to tell you how I think that dark matter is a wave. Okay, so as you just heard from Miguel, light is a wave that we're familiar with. And the electromagnetic spectrum of light waves has short wavelengths of things called gamma rays and X-rays, and long wavelengths of things like radio waves and microwaves. Radio waves have wavelengths of about 1 meter, microwaves 1 centimeter, and as you heard, gamma rays the size of an atom. We also describe waves by a similar thing called a frequency. The frequency is how quickly the wave oscillates in time. And if you have a short wavelength, you have a high frequency. So gamma rays are high frequency. And we measure frequency in this unit called hertz. So high frequencies, gamma rays are 10 to the 16 hertz, 10 to the 24 hertz. Whereas things like microwaves and radio waves are low frequencies. They oscillate more slowly. We're physicists, so we like to give symbols for everything. And we give the Greek letter lambda as the symbol for wavelength. And I'll use the normal letter F as the symbol for frequency. I'm going to have to tell you about 3 bits of physics before we get on to dark matter as a wave. Number 2, second thing I have to tell you about is that all physical systems have a natural frequency. And this is how antennas work. So here's an image of the Jodrell Bank telescope near to Manchester. And how does this big telescope detect radio waves? Well, it detects radio waves by matching its own natural frequency to the frequency of the radio waves. And this is how you get it. So the size of the dish is related to 1 divided by the natural frequency. So that means if I have a big dish, I have low frequency. That's why you need a dish this big to detect radio waves, which have a low frequency. The third thing I need to tell you about is quantum mechanics and matter waves. So you may well have heard about the famous wave-particle duality in quantum mechanics. And what does that mean? That means that in this famous experiment called the double slit experiment, I can take particles, electrons, things that were always thought of as particles, can fire them out of a gun at a screen with 2 holes in, and when they come out the other side and hit a screen, they make an interference pattern. And that is something that's very characteristic of waves. So this experiment shows you that electrons are both particles and waves. If they're waves, we need to give them a wavelength and a frequency. And we can do that. We give them a wavelength called the de Broglie wavelength, which is related to the wavelength is 1 divided by the particle mass. It's proportional to that. So if I have a higher mass, I have a shorter wavelength. If I have a lower mass, I have a longer wavelength. We can also give a particle a frequency. That's called the Compton frequency. And in this case, the frequency is proportional to the mass. So if I have a higher mass particle, I have a higher frequency, lower mass, lower frequency. We notice that a particle is a wave when its wavelength is close to the slit size, or when the frequency is low enough that we can actually measure it and we can see that time dependence. So when is dark matter a wave? Here's a cartoon from XKCD, the webcomic, with many different dark matter candidates that we've heard about, that we're going to talk about some of. So there's black holes over here that could be dark matter, but it turns out they're very much ruled out. There's some comic candidates here, space cows and obelisks. And what we just learned is long wavelengths and low frequencies. If a particle has that, we'll be able to tell that it's a wave. So we want to look at the lowest masses. This is the mass of the object here. We start off in kilograms, move down to grams, and then we move into these units called electron volts, which particle physicists like. So we go to the lightest particles, and here they are on the diagram. They're called axions. So very low mass particles have long wavelengths and low radio frequencies. So if you have a low mass particle, it will behave like a wave. And I'm going to tell you about 2 ways in which, if the particles are light enough, we can actually tell that they are waves. This is the first one. This is about dark matter waves inside galaxies. So this is an image from a simulation by Jan Veltmat and collaborators. And it shows here the cosmic web of dark matter that you just saw in Miguel's talk. But what Jan has done here is he's simulated the dark matter as a wave. So if we zoom in inside the galaxies on the nodes of the cosmic web, you can see a wave-like pattern inside here. And even been so kind to make a nice movie of this in time. And this is the inside of a galaxy in this model. So you can see it sloshing around with wave-like effects, and then it starts to rotate here with the camera. And this model would have observable effects. We could tell that these waves are there if the wavelength is close to the size of the galaxy. So galaxies are thousands of light years across. So we need a particle with a wavelength that is thousands of light years. If that's true, then these oscillations, these waves in the galaxy, can have observable effects. One of them is that if there's stars inside this turbulent medium, they will get moved around and heated up and disturbed in their motions, and we can try and look for that. The second way that we might tell that dark matter is a wave is by using a radio to look for it. So this type of dark matter, this axion dark matter, if you take an axion and you take a magnetic field, then the axion turns into a normal electromagnetic wave. And the frequencies of those 2 waves have to match because of conservation of energy. Then we use the natural frequency resonance to try and detect that electromagnetic wave. So we can have a resonance, like inside an ordinary radio, if the particle frequency matches a frequency of our antenna. This is what such an experiment would look like. So we take a resonator, a can, an antenna, and it has a natural frequency, just like the Jodrell Bank telescope. And the natural frequency is related to the length. But we don't know the mass of dark matter. So we need to be able to tune this radio. And it's just like your radio in your car. You start off, you're on 88 FM, and you keep on tuning until you get to 105 and see if you find a station that you like. If you tune too quickly, you might miss the one that you're looking for. If you tune too slowly, your car rides over before you found the station that you want. And the same is true here. We don't know the frequency of the dark matter, so we have to tune this radio. And in this case, it's done by moving some little rods inside this can. So how do we detect these dark matter waves? Well, you start off with a magnet. I said you need a magnet to turn the dark matter into a photon. You need a microwave, you need a resonator. And then you want to get rid of all your background noise. So you need to put it in a fridge. And then finally, dark matter interacts very weakly. The signal that you get out of this is very weak. So you need a nice big amplifier to amplify your signal. This idea has been around now for quite some time. And there's a very well advanced experiment that does this called the ADMX, that's the Axion Dark Matter Experiment, Axion Haloscope. We call it a haloscope because it is a telescope for looking at the dark matter halo. And this is, an ADMX exists, it's at the University of Washington in Seattle in the United States. And you can see in this diagram of ADMX, all the ingredients I just mentioned. You have a magnet, you have a cavity, that's a microwave, you have refrigeration to keep your, to make sure that it's not very hot and creating noise. And then you have an amplifier, which in this case is a thing called a SQUID, a superconducting quantum interference device. But you don't just have to have this type of microwave cavity. You can get rid of the microwave and replace it with any other type of resonator, any other thing with a natural frequency that allows you to move further in your spectrum. So the microwave can look for axions with a frequency that's close to the microwave frequency, which is about 1 gigahertz. If we want to look away from that, we need radios at different frequencies. One's in kilohertz, one's in terahertz, one's in hertz. Across that whole spectrum of frequencies, we need different technologies to try and tune to different parts of that spectrum and see if we can find the dark matter. And this is something that's being done all over the world. So I've just made a map here of the first 11 places with Axion experiments that came into my head. And you can see that this is really an international effort. We've got ADMX that I mentioned, which is a microwave dark matter radio, and that's in Seattle. We've got similar experiments to that in South Korea at the Center for Axion Precision Physics and at Oregon in the University of Western Australia. There's also many other ideas for different types of radios. For example, this one here called Casper, quite suitable for Halloween. Casper is located in Mainz in the United States, and also Mainz in Germany, and also in Boston in the United States. And Casper uses nuclear magnetic resonance as their radio. So, when is a dark matter particle a wave? The answer is when the particle has a very low mass. If you have a low mass, you have a long wavelength, and you can try and measure that inside galaxies. If you have a low mass, you have a low frequency, and you can try and measure that frequency with a radio. And you can make these statements quantitative, and I just want to show you that you can. So the dark matter behaves like a wave if it has a mass in a certain range. These are these units that particle physicists are fond of, electron volts, and there's a range of masses, a very big one, where the dark matter behaves as a wave. This is covering some 20 orders of magnitude. And to cover this spectrum, we need lots of different types of radios. So, dark matter looks like a wave if it has a very long wavelength. If its wavelength is of order the size of a galaxy, kiloparsecs. We call this fuzzy dark matter. And dark matter also looks like a wave if it has a frequency which is in a radio wave frequency where we can measure its wave-like behavior. And that's what is done by experiments like ADMX, which are actually on radios. So thank you very much. And now you're going to hear about how dark matter isn't a wave, it's a particle.
Thank you, Daddy. That was great. I think people are convinced dark matter is a wave. However, now we hear a different aspect. The next speaker is Professor John Ellis. So John thinks the darkness surrounding us is particle. Please, John.
John, you're muted.
No. Sorry about that. So I try again. Can you hear me now?
Yes.
Okay.
But you're also showing the presenter screen, I think.
Got rid of it. Is that better? Oh, no. Is that better now?
Yes, better.
Yeah. Of course, all these things work perfectly when we were practicing, but not when you actually do it for real.
I think dark matter doesn't want to be detected, so it's sabotaging our talks.
It's you that's sabotaging my talk. You're the guy who wants to detect it. Anyway, so we just heard from Doddy about waves and particles. And of course, every particle is also a wave, and every wave in quantum mechanics also produces particles. And it largely depends on what the mass is of the particle you're talking about and the corresponding wavelength. So I'm going to consider the possibility that the associated mass of this thing that we're talking about is large, and so it really does look more like a particle than one of Doddy's waves. So what should this particle look like? Well, it should not have much electric charge, otherwise we would have seen it. It's dark, after all. I say not much electric charge because there are some people who think that it might have a very small, like 1,000th of the charge, electric charge of an electron. But let's assume it has no charge. It should interact very weakly with ordinary matter, otherwise we would have detected it, either directly or in astrophysical observations, like, for example, that bullet cluster that you heard about from Miguel. And in order to behave like a particle, and in order to do its job of holding together the structures in the universe, like galaxies and clusters, it should not be too light. So what could this particle be? Well, we have what we call a standard model of particles. And this standard model is illustrated in this slide. And the particles that you see here describe all the visible matter in the universe. So for example, nuclear matter is made up out of the quarks, the yellow things at the top left. Atoms contain electrons, so they're the red thing in the bottom left. There are interactions between these particles, which are due to the exchanges of other particles like the photon that you've heard about and other particles illustrated in green. And you've surely also heard about the Higgs boson in blue on the right that gives masses to the other particles. So it's a natural question whether there's any particle in the standard model that could explain also the dark matter. And realistically, there's just one possibility in the standard model, and that possibility is provided by neutrinos, which I've circled here in purple. So the neutrino was postulated back in 1930 by Pauli. He wanted to explain the fact that when people looked at a form of weak interaction, radioactivity called beta decay, that the spectrum of the electrons coming out in beta decay were not fixed, but there was a variation in the energy of the electrons. And he said, well, maybe in addition to the electron, indicated here by the symbol beta minus, there's also another invisible, very light neutral particle called the neutrino, or small neutral one. And on the right there, you see a letter that he wrote where he proposed this idea. Okay, so could neutrinos be the dark matter? Now, neutrinos do have mass, but we know that mass is relatively small compared to, say, the mass of an electron. And this means that during the expansion of the universe, neutrinos have been moving quite fast. On the other hand, in order to form the structures that we see in the universe, we need some form of dark matter made of particles which move relatively slowly. Now, in this picture here, you see a computer simulation of what happens if you change from a heavy, slow-moving particle on the left through a sort of medium particle in the middle to a fast-moving, light particle on the right-hand side. So the slow-moving stuff, that's what we call cold dark matter, and the rapidly moving stuff, that's what we call hot dark matter. So the trouble with hot dark matter is that those fast-moving particles, like, for example, those light neutrinos, would escape from small structures in the universe, such as dwarf galaxies, and smooth them out. You see in the right-hand picture, there's lots less detail than in the cold dark matter picture on the left. So the known neutrinos cannot be the dark matter. Their masses are too small, they move too fast. That's in conflict with what we know about, for example, dwarf galaxies. So what other possibility is there? Well, maybe there are additional neutrinos remaining to be discovered. So they should not have standard model interactions, otherwise we would have discovered them. And that's what we call a sterile neutrino. So these things are expected to mix with standard neutrinos, and there's all sorts of constraints on their properties coming from the properties of neutrinos, from astrophysical constraints, and so on. And I don't have time in this talk to give justice to all the constraints, but I did want to show you this picture here, which is taken from a paper written just a few days ago by many of our colleagues at King's, who are written there in boldface, who put together all the constraints. And as you can see, there's a little white region over towards the right-hand side where this sterile neutrino might weigh a few keVs, that's a few thousand electron volts, where it might be the dark matter. Now, that's not really my favorite candidate for dark matter. And here I've got a picture which illustrates all sorts of other dark matter candidates. So right over on the right-hand side, we have black holes, which have already been mentioned. It seems unlikely that they can provide all the dark matter. And over on the left, particles with very small masses, like the axion, which Doddy mentioned, which behaves more like a wave than a particle. So Doddy has told you all about those, and so I'm not going to discuss them. Instead, I'm going to concentrate on something that we call a WIMP. So what is a WIMP? A WIMP is a weakly interacting massive particle. So when I say massive, I'm thinking of something that might weigh perhaps 100 to 1,000 GeV. That's 100 to 1,000 times the mass of a proton. So certainly way, way heavier than the axion that Doddy was talking about, certainly something that would look like a particle, and certainly something that would be very cold. But interestingly, the mass would be accessible to Large Hadron Collider experiments, as I'll discuss in just a moment. Now, such a thing does not exist in the Standard Model, but it is present in many proposed extensions of the Standard Model. And particularly, I would say, in theories that try to understand why the Winky interactions are weak and why the Higgs boson has the mass that it does. And these include models with extra dimensions of space and my own personal favorite, supersymmetry. So supersymmetry has been my favorite theory for almost 40 years now. And I must admit that in addition to my wife, it has my undying love. So what does supersymmetry predict? So on the left, we have the particles of the Standard Model that I showed on the first slide. And on the right, I have their supersymmetric or SUSY partner particles written with twiddles and with names with S's in the front or Eno at the end. And some of these particles, the ones I've just outlined, are neutral, massive particles that are possible candidates for dark matter. So how would you look for such WIMP dark matter? Well, in a moment, Joost is going to go through some of these in more detail, but just let me mention briefly the main ideas. So back in the early universe, there were probably lots of those dark matter particles which annihilated to make Standard Model particles. What we could do now is, in a particle collider, we can collide Standard Model particles and hope to produce pairs of dark matter particles. Or we could go deep underground and look for the very rare scattering of dark matter particle of a Standard Model particle. Or we could look in cosmic rays for possible annihilations that might be occurring nowadays. So for many years, I was working at CERN, the big particle physics laboratory outside Geneva. And for that reason, I've been thinking a lot about what one could do with the Large Hadron Collider. So you see it here. Well, actually, you don't see it. This circle marks the location of the collider, which is actually in a tunnel about 100 meters underground and about 27 kilometers in circumference. And inside that tunnel, the experimentalists collide lots and lots of particles, mainly protons, and then they look at the collisions of those protons to look whether interesting new particles come out. So top right, we have a cutaway view of the ATLAS experiment, which together with the CMS experiment, bottom left, discovered the Higgs boson a few years ago. And these experiments are now looking for dark matter. But by the way, the L in LHC stands for large. And that refers not only to the collider itself, but also to these experiments. And if you look very carefully in the top right-hand picture, you can see a person who is not a Lego person, that's a real full-size person. So experiments at the LHC, and I think Joost is going to describe this in more detail, have been looking for supersymmetry, haven't found anything else new beyond the Standard Model, but they're still looking. There's all sorts of corners in the possible masses of supersymmetric particles and other properties that have yet to be explored. And the LHC will continue to try to produce dark matter particles in the coming years. It's expected that it's going to produce something like 20 times more data than what we've got so far, and there's quite a chance that we may see supersymmetry in the coming years. So here I have a picture which you probably all know, but of course what you don't know is what they were discussing. And the people on the left, those are the people who believe in supersymmetry. And the person of the right, he doesn't believe in supersymmetry. So I'm sure that I've convinced you that you should believe in supersymmetry like any sensible person. So that brings me to the end of my talk. The summary is very, very simple. As you heard from Miguel, most of the matter in the universe is not the visible matter, but is some form of dark matter. And the one thing that we can be sure about is that that dark matter is going to sink the standard model. Thank you.
Thank you, John. Is that possible to see your costume?
So people don't seem to be too sure what my costume is, but the giveaway is the 19. This is my COVID costume. And unfortunately, when I'm sitting down, you can't see my t-shirt. What I can do is I can wave my sickle or scythe. And I would have you notice that this was actually made in China.
Thank you. Thank you for a great costume and a great talk. Okay, so the next speaker is, excuse me. Sorry, we are having a meeting, please. Excuse me. Hey, what are you doing? Hey, no, hey.
You want my sword to get rid of him? Here's the sword.
Yeah.
Who are you?
Now I'm the new chair. I took this position and I wear the mask. So I introduce next speaker. Next speaker is the scientist, the hyper scientist working on hyper Kamiokande. Everyone welcome, Dr. Jost Migenda.
Ooh. Hello, everyone. I'm Jost Migenda, and when I don't float through the bullet cluster, I'm a postdoc at King's looking for neutrinos. And after Doddy told you dark matter is definitely a wave, and John told you, no, it's a particle, I'm here to tell you it's complicated. So, you know, we need to search for it. So to prepare for this talk, I did a search for dark matter on Apple Music. Here's what I found. I found a contemporary jazz album called Dark Matter. And I listened to it and it sounded, you know, nice, smooth, had a jazzy flow to it. So that's clearly a wave, probably an axion. I also found this metalcore album called Dark Matter. And that's more high energy, heavy, clearly a WIMP. And then I also found whatever the heck this is. So clearly there are many kinds of dark matter. And to search for them, we need many different experiments. So I'm gonna tell you about just some of them today. First, let's try looking for wave. And the basic effect we use is always the same. The one that Doddy already told you about, where an axion, when it enters a magnetic field, can turn into a photon, which we can then detect. And the easiest way is just to have your cavity, put it into a giant magnet, And that looks like one of these experiments that Doddy showed you. But you can also use the same effect in lots of different setups. For example, here's an Axion telescope, which is located at CERN. And you can see there's guide rails here to keep it pointed at the sun for hours a day, so that if axions are produced in the sun, they will enter this telescope, and inside this large blue magnet, they will hopefully turn into microwaves, which we can then detect. And you can also do a third type of experiment, which is called shining light through a wall, where you basically use this Primakov effect twice. So you send a laser through a magnetic field to turn some of these photons into axions. The axions can then go through the wall, which light usually can't. And then on the other side, there's a second magnetic field, which turns the axion back into a photon. And this experiment, I think, is really cool. For one, because it's shining light through a wall. But also, if you look at the technology it's using, some of these dipole magnets here to create the magnetic field are from an older proton accelerator. And these optical cavities for they use here for amplifying the laser. These use some techniques that we've developed for gravitational wave detectors. So this is really lots of different technology coming into one experiment. So many different ways of searching for axions, and hopefully one of them will be successful. But now for the rest of the talk, let's try looking for particle. And John already told you that the particle we'll be most likely to find is a WIMP, or weakly interacting massive particle. And there's 3 common ways to look for WIMPs. They all look like this. The only difference are you can two maybe other standard model particles colliding, annihilating, and turning into WIMPs. And turning into a pair of WIMPs. On the other hand, if time goes from the top to the bottom, you have a quark and WIMP bouncing off each other and going their way. And finally, if time moves from right to left, you've got 2 WIMPs coming in, annihilating, and then turning into a pair of standard model particles. So you can make WIMPs by colliding standard model particles. You can shake WIMPs by letting them bounce off known particles. Or you can WIMPs by letting them annihilate and looking for the products. So let's start by making WIMPs. And our best tool is the Large Hadron Collider, which John introduced. And this, what we have here is an image of an actual event at the Atlas experiment. So there's 2 protons coming from both sides, colliding right here in the center of the detector. And then you've got sprays of particles going out. And you can see a particularly large kind of jet of particles is moving here towards the top, and it's depositing energy in the detector. That's shown by these green and yellow blocks. But we know that energy and momentum are conserved, so there should be an equivalent jet going downwards. But there isn't. So what's happening there? And the answer is, this might be a WIMP. So there is another particle going downwards, so that energy and momentum are still conserved, but we just don't see it in our detector because it is so weakly interacting. So that may be a WIMP, but on the other hand, it may also be a neutrino. And by looking at just this one experiment, this one event, we can't tell for sure. So what we need to do is take lots and lots of data, look for all events like this, count how many we find, and then calculate how many we would expect to see if there are only neutrinos, no other particles, no WIMPs. And if there's a different more of these events than we'd expect, then we've discovered a new particle. So that's how to make WIMPs. Next, let's shake WIMPs. Let's let them bounce off particles like atomic nuclei, and then look for this nuclear recoil we get from this collision. And there's 3 different ways we could detect those. And modern experiments typically use a combination of 2 of them. For example, the CREST experiment is using these calcium tungstate crystals, which produce both scintillation light, which you can see here in the photo, the blue glow. But they're also running this experiment at extremely low temperature, just 10 millikelvin. So that even this single nuclear recoil can cause a measurable increase in the temperature. Other experiments like CDMS or ILWeiss use germanium or silicon crystals. And these also observe a temperature increase, but they also observe ionization in the material. And finally, a 3rd type of experiment uses liquid noble gases like xenon. One of these experiments is called Xenon 1 ton, and you don't get a prize for guessing how large the detector is. So what these do is, if a particle like a WIMP comes in and collides with a nucleus in the detector, you can see on the left, there's this immediate flash of scintillation light. So the photosensors on the top and bottom of the detector see a little flash of light. At the same time, the xenon atoms are ionized. So you get this little cloud of free electrons, which slowly drifts to the top of the detector and causes a second signal there with a bit of a delay. And by combining these 2 signals, the small instantaneous flash of scintillation light and the later but much larger signal from the electrons, these experiments can tell apart a WIMP interaction from lots of backgrounds like radioactive decays, for example. And then our final way to detect WIMPs is to break them. So to let 2 of these WIMPs annihilate and form a pair of standard model particles. Now, these particles could be almost anything. They could be X-rays or gamma rays. They could be positrons. They could be neutrinos, which are my personal favorite particle. So there's a lot of different channels to look for them. And we usually look at places where there is a large concentration of dark matter, like the galactic center, or dwarf galaxies, which are these galaxies that contain a lot of dark matter, but so little visible matter that, if we see any signal, like a gamma ray signal from there, there's really nothing else that could produce it. So there's very little known background. And finally, a bit closer to home, we could also look for dark matter that's accumulating at the center of our sun. Now, what would such a signal look like? Well, here's a potential signal in gamma rays from the galactic center. And you can see in this plot the y-axis shows the flux of gamma rays as a function of energy. And this shows 5 different regions. The first one on the top is a very large region around the galactic center, while the last one at the bottom is a very narrow region, almost directly around the galactic center. And because it's so small, you can see there are very few observed gamma rays. So the error bars are really large here. But if you look closely, especially in the region 3 and 4, at around 130 GeV energy, which is this gray region here, you can see there's a bit of a bump in the spectrum. So there are a few more gamma rays than we'd expect with this energy. And this could be evidence for dark matter. This could be a WIMP with about this 130 or so GeV energy. So a bit more than 100 times the mass of a proton. Now the problem is, as you can see here, this is still very uncertain. And even the author himself in this paper and in the title calls it a very tentative signal, and says it's based on only 50 photons, and it will take years of additional data taking to clarify this. Now, I really like this paper because when it came out in April of 2012, I had just started my bachelor thesis, which by complete coincidence was on gamma rays from annihilating dark matter. So back then I was young and naive. And when I saw this paper, I was really excited because I thought, oh my goodness, this is it. We've discovered dark matter. And yeah, I was a little disappointed when I learned this is not the first such hint, and it's also not the last one. So there's been a bunch of similar hints since then. These are just a few examples. So you can see there's several of these hints, but there are also large uncertainties because we don't know where exactly to look, whether dark matter is really concentrated in a very narrow region around the galactic center, or whether it's more spread out. And we also don't know whether there might not be some regular astrophysical processes which we don't quite understand yet, but which could fake such a signal. So there are many uncertainties, and I guess we'll have to keep looking. So in summary, whether it's a wave or a particle, it's super complicated. We've got many different candidates: the smooth, jazzy axion, the high energy, heavy WIMP, or it might be something completely different. And there are many different ways to search for all of these different particles, because only if we explore all the methods, explore all the parameter space, we will have a chance to find whatever it is. Thank you. And back to our chair.
Thank you. Thank you, Dr. Yost. That was a great talk. Now, I want to introduce my fellow wrestler speaker. In fact, I'm preparing another 666 speakers. So all night, you wake up and listen about dark matter. Wait, who is that? Someone is outside. Hey, excuse me. No, you can't do this. Ooh, 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 ooh. Bam, 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 bam. Pew, 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 pew.
Who's next?
Is our chair there? Seems to be
He must have been got.
abducted.
He must have been abducted.
Who is that?
Oh, sorry, I was a bit late. Intruder was removed. So now, thank you for staying all night for our event, and we'd like to move to the Q&A session. I'm the new chair, the pirate. Okay, so let's go through some of the questions we just received. And also, yeah, how about this one? Does dark matter interact by itself?
That's a very good question. We don't really know. Oh, sorry, I have a guest here, a guest speaker. Yes, so we know that dark matter interacts very weakly. Well, we don't know. We think it might, and that's how we expect to measure it, as Joss explained. Whether it interacts with itself or not is still a subject to debate. But for example, we can use one piece of evidence that I showed earlier, the bullet cluster, to put constraints on how much does dark matter interact with itself. So we don't have clear evidence that it does, but if it does, we know that it cannot be above a certain value. So we can use the evidence that we have to put constraints, but it's not clear yet.
And I think we should also say that, you know, in these WIMP theories that we heard about from John and Jost, the dark matter actually necessarily interacts with itself, because that's how we get it in the early universe. We saw in John's diagram, right, that you take two dark matter particles and you annihilate them into ordinary particles. So it does interact. So in that theory, it really does interact with itself. And with axions, it also does. There's also a self-interaction, but the amount of interaction that you need to get the dark matter in the first place is very, very small, and is too small to see in something like the bullet cluster. So in most cases, it does interact with itself, but it's often very, very small.
I think that we know from the sort of experiment that Joost was describing that its interactions cannot be stronger than conventional weak radioactivity, and it could be a lot lower than that. I mean, some of the models that I didn't discuss have interactions that are way, 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 way weaker.
Great, thank you very much. Let's moving on to the next question. There are few people asked the same questions. Is the dark matter more promising than the modified gravity theory? Well, why people so into dark matter as a, sorry, maybe the question is different. Why do you think the dark matter is a particle or wave, but not this modified gravity theory? What is more, why people think it's more promising?
So I would say that modifying gravity is a much more radical idea than just postulating a new particle or even new waves through the universe. Our theory of gravity, general relativity, works incredibly well, and there are all these gravitational wave experiments that confirm it in all sorts of new physical situations. And the sort of gymnastics that you have to go to modify gravity in such a way that it's compatible with all the constraints, it looks to me really, really ugly and implausible.
I mean, yeah, but I think also, you know, it's observation driven. I mean, as you said, there's all these hoops to jump through, but for me, it's the cosmic this thing called the cosmic microwave background radiation, famously measured by the Planck satellite, the WMAP satellite, and many others. And dark matter can explain the large scale structure of the universe. What Miguel showed, these the cosmic web and there is no theory of modified gravity. And you know, I've looked at I've looked at a lot. I'm sure we all have that can explain that. There is no consistent modification of gravity that explains the cosmic web and the cosmic microwave background. It just doesn't. There is no such theory. And people, it's not because people haven't tried. People have tried very hard. My PhD advisor has worked on this. My previous PhD advisor, many other people.
I think what's really convincing is the kind of breadth of evidence for dark matter. So you see it on cosmological scales in this cosmic microwave background. You also see it on clusters, in clusters of galaxies, which Miguel talked about earlier, as well as on the scales of single galaxies with these rotation curves. So having just one new particle, additional feature, which you add to explain these three different phenomena across all different scales is really powerful.
And just to finish that point, and also following what Dodi said, a lot of people have tried and they keep on trying. So, which is good, right? We need every possible theories to follow what they believe it might be dark matter. So modified gravity theories should be there and should be explored. But so far they have failed to explain all kind of evidence that we have for dark matter as a particle. Just wanted to finish with that.
Great. Thank you, everyone. So let's move on to the next question. So there are several similar questions. What is the most promising way to detect dark matter? And I think question was more specific. What is the most promising way to detect dark matter halo?
Well, it depends a little bit on what you think that this dark matter is. So, for example, if you think it's a WIMP, then what you can do is you can look for instances where some dark matter particle going around in the halo collides with another one, and they have a sort of one-night stand, which produces standard model particles. And as Joost was discussing, these collisions of dark matter particles out in the halo could produce particles that we can see, like, for example, positrons, or he mentioned gamma rays, or even neutrinos. So if you believe that dark matter is a massive particle, then I think that will be a promising way to go.
There's a similar phenomenon that can happen for axions. So just like John said, and Joost said, you can have dark matter particles out in the halo. If they're heavy particles, they annihilate into gamma rays that you can try and detect. If you have axions out in the halo and you have a magnetic field, and we know that the galaxy has a magnetic field, then those axions in the magnetic field of the galaxy can convert into radio waves. And you can try and look for those with radio telescopes. So something like the Square Kilometre Array, which is being built in South Africa and Australia to do radio astronomy, but you could use it to look for axions. So yeah, if you're thinking about detecting the halo, these are both very promising ways.
And of course, if you ask any experimental physicist, the most promising experiment is whatever they are working on right now.
So
Okay,
the one working on super Kamiokande and hyper Kamiokande, these are very good for looking for neutrinos. So look for neutrinos from annihilations of dark matter particles, maybe.
Absolutely.
It's great. Let's move on. So the next question. So the question is, does dark matter moving create a gravitational wave? But I want to expand a little bit. Is dark matter, or this science about dark matter, does do anything with gravitational wave?
Well, any form of matter generates gravity, and when it moves, it can maybe make gravitational waves. Slightly more technical, you have to have a changing quadrupole moment, which is sort of like a rotating rugby ball, for example. But no, certainly dark matter particles could do that as well as stars do it. And of course, when neutron stars do that, they certainly produce gravitational waves, and we've seen gravitational waves coming from the mergers of neutron stars. But the gravitational waves produced by individual dark matter particles are going to be incredibly weak. However, it's possible that there might be clumps of dark matter which would look a little bit like black holes. And so maybe they could annihilate and produce gravitational waves when they do. And people are sort of looking at these gravitational wave signals being observed by LIGO and Virgo to see whether there's some deviation from general relativity, which could be explained because actually they're not gravitationally bound black holes, but actually there's some sort of dark matter clumps.
And also, I think, the dark matter candidate we didn't talk about, because in the XKCD slide that I showed, it's very highly constrained, is black holes. There is a space where dark matter, where only a small amount of dark matter, actually, we know it can't be all of the dark matter, but where a small amount of dark matter could be black holes. And actually, when the gravitational waves were first observed in LIGO, the theory went around for a while that, hey, these were masses of black holes that maybe weren't expected from stars, and maybe they could be dark matter black holes. Now, it turns out that doesn't work. Not all the dark matter can be black holes, but it could be some of it. And in that case, we very much could see those gravitational waves.
And those black holes have a slightly more kind of physicsy name. They're called massive compact halo objects, or MACHOs for short. And actually, I have a question to the other speakers, especially to John, maybe, because you were probably around when those terms were invented. MACHOs and WIMPs, which of them came first?
So WIMPs came first, and then MACHOs came along as a reaction to them. But I'm not really a macho sort of a guy. I mean, I'm not saying I'm a WIMP either, but I'm certainly not a macho.
Great, thank you. So next question is there any experiment to look for dark matter in UK?
Yes. Well, so at least there are experiments of the sort of type that Joost was mentioning that are looking for the scattering of WIMP-like particles. And there's a mine in the north of Yorkshire called Boulby, where there's been a series of such experiments. And then there's an idea that some of us are working on at King's, which it would be to look for these waves that Doddy likes. And this is a project which uses a technology a little bit similar to the LIGO Virgo gravitational wave detectors. So they are based on laser interferometers. And so the idea that we're interested in is to use interferometers using atoms. And we plan to build a detector for such things in Oxford. So it's not operating yet. It'll be a few years before it's operating, but that's certainly something we're working towards.
Maybe a point that is important to mention. A lot of this experiment for direct detection that Josh was describing, a lot of them are, for example, in Italy. One reason because of this is that you need a strong shielding. So you use basically a whole mountain to shield from cosmic rays and all sorts of backgrounds. So that's the reason why a lot of these big experiments are in places like Italy. Or underground mines, for example, in the US.
Okay, so let's move on next one. There are several similar questions, so I put summarize them together. Is dark matter and dark energy related, or do they do anything with each other?
So,
Who should start? This is a long one.
okay. No, I've got a short answer. Maybe
Perfect.
I'll start and then you can expand. Yes, so that's quite a common question. So are dark matter and dark energy related? And my kind of standard answer is, well, they only share a first name, not a last name. So the dark matter and dark energy are about as related as Donald Trump and Donald Duck.
That's a great answer.
For the slightly more physicsy answer.
That's a great answer. When I was presenting, I was very careful to, when I was talking about the relation between normal matter and dark matter, and I use 15% and 85%, I was very careful to take that as the big pie of matter. The thing is that, as we know since Einstein, matter and energy are just two forms of the same thing. That's what this famous equation E equals mc squared tells us. So you can put everything in the same sack. And when you do that, then turns out that dark energy, which is a form of energy, it's way more or way larger than normal matter. I don't remember what's the current percentage, but it must be 70% or something. The difference is, or what dark energy does, is that it's our way to explain why the universe is expanding at an accelerated rate. We don't have any way to explain this. So we know even less about dark energy than we know about dark matter. And in principle, no, they are not related, but some people have tried to relate both, so far unsuccessfully.
So you go ahead, John.
Yeah, so phenomenologically, the key difference between dark matter and dark energy is that dark matter clusters, and we heard earlier on from Miguel, for example, how important dark matter is in forming clusters. And that's because it gravitates in the same way as regular matter does. But dark energy gravitates in a completely different way. In fact, in some sense, rather than being attractive, it's sort of repulsive. And so it doesn't cluster. It just spreads out, and it's uniformly spread throughout the whole of space. And it tries to get away from itself, and so it actually causes space to expand. So its gravity behavior is completely different.
So I'll expand briefly on one of the things Miguel said, that people have tried to relate these things. And so John just said that dark energy is like something that's spread completely over all of space. Well, okay, dark matter is a wave, right? So what if dark energy is a wave? It's one with a wavelength that's as long as we can see, as big as the visible universe. And I'm an axion fanatic, as I've said. They can't be the same axion. So just like we have in the standard model, John said, we've got electrons and muons and tau particles, similar particles, different mass. It is possible that you can have an axion, and there's one axion and it has a mass that's correct for it to be the dark matter, and there's another one that has a mass that is correct for it to have this very, very long wavelength and look like dark energy. I actually don't think that's a very likely explanation for dark energy, but it is possible to have theories where they're related in the sense that it's a two types of similar particle or similar wave, if you want. But there's no compelling evidence for any of those connections.
Okay, let's move on. So there are similar questions. So again, I want to put all together. So in the beginning, in the Miguel's talk, there was a story, this dark matter get together in the early universe, and that makes structure of the galaxy because normal matter get together after dark matter. So this suggests, so dark matter is kind of a primordial particle, it existed early universe. Is that dark matter amount or property changing over time? Is there more dark matter in the past than now, or how this story goes with time?
So we don't think that the properties of the dark matter particle change significantly with time, at least if it's a particle. But we do believe that the density, the number of them per unit volume of space changed. So, for example, in the early universe, they would have been rushing around and annihilating with each other, as Joost mentioned. So the number of them would have been going down, and of course that process is probably still continuing today, although at a much lower rate. And of course, as the universe expands, even if you had a fixed number of dark matter particles, they would get separated more and more from each other, so that the local density of them in space would gradually go down. But the properties of the individual particles would not change.
So, I mean, a very important thing that the people who've asked this question point out is that dark matter had to be around in the early universe. And that's something that Miguel told us. And that's one of the reasons that we know that that it's not modified gravity, that it's dark matter. We actually know from these observations of the cosmic web that dark matter had to be in the early universe. It's something that's like primordial. And that's what any successful theory has to do. It has to explain where that primordial amount came from. And then, as John said, the amount of dark matter has to be pretty much, it has to be, once it's made, the amount doesn't change very much. And if it did change too much, then the observations of the cosmic web, for example, wouldn't work. If you change the amount of dark matter by, I'm gonna guess, if you changed it by a few percent in any time during structure formation, you wouldn't get the right cosmic web. So it's important that it's there in the early universe, and it's important that its number doesn't change appreciably over time.
Okay, great. Next question. Is dark matter actually like several different things or just one type?
That's a good question. We don't know, and yeah, that's a problem. It's perfectly valid that dark matter could be both a wave and a particle, or more things that we haven't covered today. The problem with that is that it starts to get convoluted, and our approach in physics is usually to start from the simplest possibility, is what is called Occam's razor. But nothing prevents the fact that dark matter could be perfectly well more than a type of particle. If it is, we are in a bit of trouble because all our constraints usually in the different types of dark matter assume that it's just made up of this one type, right? But nothing prevents it to be different types.
But it is also something that you can test, that you can test in some cases. So it's something that I've worked on for a number of years, is if the dark matter has a wavelength that's really big, then we would have noticed. And in that case, you can actually limit the fraction of it. So there's a range of possible wavelengths over which we can say, actually, no, it's one thing to within an accuracy of about 2%. Of course, it could be, two different types of WIMPs, and we can't tell those apart and this is with observations of structure formation and the cosmic microwave background. If it was two different WIMPs with slightly different masses, yeah, or 3 or 4 or 5, we can't tell. But we know that less than 1% is a mixture of very long wavelength particles, and just like we know less than 1% is black holes with a certain mass. So you can entertain theories where there's a mixture and limit that mixture, but in a lot of cases you just couldn't tell.
It's perhaps worth commenting that, of course, ordinary matter, ordinary visible matter, has various different components. So by far the most important part is nuclear matter. And the mass of an individual nuclear particle, like the proton, is something like almost 2,000 times that of the electron. So you could say that the density of ordinary matter has two components, but one component is much, much bigger than the other. And I think that generically, that's sort of what I would expect also, that if there were two components for the dark matter, it would be rather unexpected that the two of them would be comparable. I would expect one maybe to dominate.
Thank you. So it's almost a time. So maybe we can wrap up, and it's a final question. This is again combination of many questions. For example, there's no WIMP search. WIMP search is failing. What are you gonna do? There's no SUSY. What are you gonna do? So this is a question for all of the speakers. So what is the most promising candidate of dark matter, and how we find it?
Let's take it in turns. Who wants to go first?
You can go first.
Okay, well, I'll take the party line. That a very promising candidate is the axion, and it does two different things. It's dark matter. It also solves the symmetry problem of the standard model of particle physics, just like actually supersymmetry does, but a different symmetry problem. And it's not ruled out. There's a lot of space in which axions are still allowed, and there's all these new experiments that can look for them. As Joost said, every experimenter's favorite experiment is their own one. I'm a theorist, but there's all these experiments that I showed you. I think it's very promising. Yeah, that's my favorite.
Yeah, if I might comment, I try to remain agnostic regarding the nature of dark matter. We don't really know what it is, but certainly the candidates that we heard today, both axions and WIMPs, or other types of matter or particles, let's say, in the range can be possibilities. I think that as physicists, we need to. This is a bit like a gamble, right? You go with an experiment, and you have to put your money on this experiment. But we try to cover as much bases as possible. It's not looking a needle in a haystack, it's looking for a needle in a bunch of haystacks. So you have to commit with one and then try to complement these searches. And that's why we have such a large array of experiments. I personally don't have a favorite, so I would like not to commit with when it comes to dark matter.
Yeah, well, I guess I nailed my colors to the mast, right? I talked about WIMPs. I like WIMPs rather than waves. And among WIMPs, as I said, I've remained faithful to supersymmetry for many years. Probably I shall be buried still dreaming of supersymmetry. But anyway, that's what I'm still interested in.
And yeah, like Miguel, I'm pretty agnostic, but I think it's really important that we try all of these different experiments, searching for all kinds of different particles, because even if it's one that or particles or waves or whatever, because even if it's something that we might not expect, we might not think is likely, we'd still want to find it if that's a true one. And I think the nice thing is that there's no kind of, we don't have to decide between doing one experiment or the other. And in fact, the experiments can learn from each other. And I talked about this with the shining light through a wall experiment, which uses a lot of stuff we learned from gravitational wave detectors. And I'm sure there are lots of other examples of this. So by going into many different directions and exploring all of it, we get a lot of, this vast vat of knowledge that we can combine in different and maybe unexpected ways.
If I'm allowed a final thought, looking into the future, measuring or having a confirmation of a detection, it's just going to be the first step. Because after this, whatever it is, we'll need to analyze its properties, and I'm sure that, as just mentioned, the interconnection or the feedback between different experiments is going to prove essential.
Great. So I think it's almost time. So maybe this is the end of today's event. So thank you everyone attending to this great Halloween night. And we are pretty sure we will have a Dark Matter Day 2021. Hopefully next time we can invite all of you again in lecture theater like we did last year. But we'll see how this goes. So thank you for all speakers one more time. And thank you everyone for attending tonight, and have a good weekend.
Thank you, everyone.
Thank you. Thank you
Thank
to
you.
Kay for organizing things.
Thanks a lot
Thank
to
you.
our multifaceted chairman.
Bye-bye.
Bye-bye, guys.
Bye.